It's my pleasure to introduce the last lecture of the first day of the conference celebrating Andrew's 60th birthday. Our last speaker comes to us from very far away, from University of New South Wales in Sydney, a very beautiful place. Alina Ostafe will speak to us on equations and character sums with matrix powers.
Ken, do you hear me well? Yes. Well, I want to start by thanking, first of all, Andrew and all the organizers for giving me the opportunity to speak here. It's such an honor. In fact, I met Andrew and many of you for the first time here, and it is such a pleasure, so thank you so much. So today I will discuss some recent work with Igor Sparlinski and Felipe Voloch about equations with matrix powers, and also I will discuss various applications including bounds for character sums with such matrix powers. So let me start by setting up the notation and some motivation. In this talk, GL of N and Q and SL of N and Q will have the usual meaning. So we will work with n times n matrices over a finite field FQ, and Q is a power of a prime P. So in this talk, P is always a prime. For a matrix A, which is invertible and a positive integer nu, I will denote by Q nu of N and Q here, sorry, to be the number of solutions to this equation in two new variables. So we have x1, x nu, running from 1 to the order, multiplicative order of the matrix. And we are interested to give non-trivial bounds for this number. So the trivial bound is, of course, tau to 2 nu minus 1. And we are especially interested in the case of nu equal 2 and nu equal 3. So for nu equal 2, I will denote this number of solutions by E and Q. So here we have 4 variables. And for nu equal 3, I will denote this quantity by F. And E and Q is also commonly known as the additive energy of the multiplicative group generated by A. So E will represent the number of solutions in 4 variables, F in 6 variables. Let me say a few words about previous work. So I will start with the scalar case. So the matrix A is now an element of the finite field, and I will mention, I will limit myself to the prime case of order tau. And there are various results better than what Veil gives. And maybe the first result is given by Garcia and Voloch in '88. And he proves that the number of solutions in 4 variables is at most tau to 8/3 when tau is in this range. Later on, Heth-Brown and Koniagin, they improved the bound to tau to 5/2 in this range. And Koniagin gave a general bound for the number of solutions in 2 new variables. So we have here the trivial bound, and the saving is tau to -1/2 to nu minus 1. And there were several other improvements based on additive combinatorics by Shredov, and maybe the best bound is by Murphy, Rudnick, Shredov, and Steinikov in 2019. And they proved that the additive, so they give the following improvement over the bound of Heth-Brown, which is, so the saving over that bound is tau to -1/20. And there are also various results over arbitrary finite fields, but they are more difficult to state. So as I said, I will limit myself only to the prime case. So now let us go to matrices. And the first result in this direction was by Kurlberg and Rudnick in 2001. So for a matrix A of determinant 1, so 2 by 2 matrix, they proved that the additive energy is at most 3 tau square. And this is a tight bound because one can easily show that one also has a lower bound of the shape tau times 2 tau minus 1. We also link such bounds to the study of quantum ergodicity of linear maps in residue rings, which I will mention very briefly at the end of my talk. Bourgain, soon after, building on the work of Kurlberg and Rudnick, he proved that for a prime Q and tau larger than p to the epsilon, so he gave an asymptotic formula for the number of solutions in two new variables to the matrix equation that we have seen at the beginning. So here we have what we expect, and this is the error term. For new, at least for new larger than nu0, where nu0 and delta depend on epsilon, but not in an explicit way. I should also mention that I think that this should work also for n times n matrices. In two particular cases, in the split case, so when the characteristic polynomial of the matrix completely splits or is irreducible. So perhaps this will work. It has never been written. Are we interested in these matrix equations? Well, I think the problem is just beautiful. We want to improve and extend the result of Kurlberg and Rudnick. And in particular, we give a non-trivial bound for any dimension and arbitrary finite field. And there are also various applications of these bounds for such matrix equations. And I'll mention a few of them. So first, we are interested in improving the bound of Korobov on additive character sums of this form. So here, psi is an additive character, and bold A and B are vectors, and we take them such that this multiplication makes sense. So A here is a row vector and B is a column vector. We also give bounds for Kloosterman sums over small subgroups, and this in turn has also application to other problems. For example, to study the distribution of palindromes in arithmetic progressions, or to study the equidistribution of some points on the torus. We also have applications for additive properties of matrix orbits, which I will very briefly mention. And as I already mentioned, one also uses such bounds to study the equidistribution, to give explicit equidistribution results for eigenfunctions of linear maps over residue rings. Let me now start by telling you what type of results we obtain. So I will start with a general bound for the additive energy. So let me recall that for A, an invertible matrix, E and Q represents the number of solutions to this matrix equation in 4 variables. And the result that we obtain is the following. Let A be diagonalizable. Then we have the following bound. So here we have the trivial bound tau to the 3. And the saving comes from this term. And this bound works for any matrix A. And when we are in the irreducible case, that is the characteristic polynomial of the matrix is irreducible, then one obtains a better bound, which is of this shape. Of course, here T hurts. So T here, T is the order of the determinant. Again, T is the order of the determinant, and tau is the order of the matrix. And this will be fixed notation for the rest of the talk. So T here, of course, hurts us. The bound is best when T is 1. So let me mention that when we are in the SLN case, the bounds read as follows. So E and Q is at most tau to 3 minus 1 over n times n minus 1, which is for any SLN matrix. And in the irreducible case, we have this. So this is the case of the additive energy. We have 4 variables. Now let us go to the next step, that is 6 variables. So let me recall that F and Q is the number of solutions to this equation in 6 variables. And of course, if we have a bound for the additive energy, we can fix now 2 variables, x3 and x4. And expressing, we reduce the problem to counting the number of solutions to this inhomogeneous equation, where B here comes from fixing x3 and x6. And expressing this, the number of solutions to such equation using character sums, we obtain the following inequality between the number of solutions in 6 variables and the number of solutions in 4 variables. And in particular, when n equal 2, we saw that Kurlberg and Rudnick, they gave a tight bound for the additive energy, which also leads the bound tau to the 4 for the equation in 6 variables. But what we want is to obtain stronger bounds than what this relation between F and Q and E and Q, this inequality gives us. So we obtain the following result. Let A be a, so we are in the same setting as Kurlberg and Rudnick. Let A be an SL2 matrix, which is diagonalizable. And now we have two cases. When the characteristic polynomial splits, so we are in the 2 by 2 case, or is irreducible. When we are in the splitting case, we obtain this bound. And when we are in the irreducible case, we obtain this bound. And we note that these bounds are non-trivial for any tau, and in particular, they improve the previous bound that I mentioned that follows from Kurlberg and Rudnick for tau between p to the epsilon and p to the 1 minus epsilon with some fixed epsilon. So let me start now by saying a few words about the idea of the proofs. So I will start with the general bound for the additive energy. We have this equation, and we want to count the number of solutions to this equation. And this equation will lead to an equation. Now, why n and not n squared? We assume that the matrix A is diagonalizable, and hence writing A as an invertible matrix U, D, U inverse, where D is the diagonal matrix with the eigenvalues of A on the diagonal, then we can translate this equation into this equation. And hence, looking at the diagonal elements, we reduce the problem to counting the number of solutions to this system of equations. So we have n equations in 4 variables. All right. Now let us fix x3 and x4 here in a trivial way, in tau square ways. And those we obtain tau square systems of equations of this form. So we have the variables x1, x2, and these psi j are just elements in FQ, and we can also assume that one of them is non-zero. Otherwise we count the number of solutions when it's 0. Okay, so now we have to count the number of solutions to this system. Now let us take the product of all these equations. And in fact, we take the product of psi j minus lambda j times x1. Why we do that? Because this will give us the product of all these terms. And this will be just the determinant of A to x. Now recalling that T is the multiplicative order of the determinant, then we reduce the problem to counting the number of solutions in x1 to T such equations. So for T distinct values of psi 0. And any non-trivial bound for the number of solutions to this equation will give a non-trivial bound to the additive energy. Now, one can also remark that the number of solutions to this equation actually counts the number of zeros in a linear recurrence. If you expand this product, you obtain a linear recurrence of order 2 to the power n. But this will lead to weak results. So we don't want to go this way. Instead, we use this product structure, and one can prove the following result for the number of solutions to this equation. Suppose that L is the maximal order of the eigenvalue. So say lambda 1. And as I mentioned, we assume that psi 1 is not 0. Then the number of solutions to this equation is at most, well, tau is the trivial bound. And then we have L to minus 1 over n, where tau here again is the order of the matrix A, which is also the LCM of all the orders. And the proof behind this result follows exactly the same ideas as in Canetti, Friedlander, Koniagin, Larsen, Lehmann, and Sparlinski, where they give bounds for the number of zeros of sparse polynomials over finite fields. All right, so we have a bound for the number of solutions in x1 to this equation. And plugging in the discussion that we had, we deduce that the additive energy is at most this quantity, depending on the order of the determinant of the matrix and the maximum order of the eigenvalues. So to conclude, we only need to give a lower bound for L, and then we are done. To obtain and one can give very easily such a lower bound. So L is at least maximum tau to 1 over n, or tau over t to this power. And plugging in this inequality, one obtains the bound that I mentioned at the beginning. So this is the case for the additive energy. Now let us move to and let me just mention here that I said that in the irreducible case we obtain a better bound. Why is that? Because in this case, all the eigenvalues have the same multiplicative order. So then L is just tau. So just plug L tau here, and then you obtain the better bound. And now let us move to 6 variables, and our result holds for n equal 2 and in the prime case. And as I mentioned, we have two cases, the split case and the irreducible case. So in the, I'll just mention the split case. So matrix A is in SL2, and those the eigenvalues are of the form lambda and lambda to -1, and they are in the finite field FP, because the polynomial splits. And the initial equation, this will lead to this system of equations in x2, x1, x2, x3, x4, x5, x6. So we have this system. Now let us fix x3, x4, and x5. And let me denote A to be this term minus these two terms, and B to be this term minus these two terms. And let us take the product of these two equations. So we take lambda x1 plus lambda x2 plus A will be lambda to the power x6. And we multiply this with this plus B, which will be lambda to minus x6. So this multiplied with this will give 1. And we reduce the problem now to counting the number of solutions in x1, x2 to this equation, which can now be translated to counting number of FP rational points on an algebraic curve, which in our case is given by this equation, where S is P minus 1 over tau. We are interested in the case when tau is small, which means that S is large. And in this case, the classical methods, that is veil bound, is not working. And instead, we use a result of Woloch, which says that if P is a prime and F is an absolutely irreducible polynomial of degree at most P, then the number of FP rational points is at most this quantity. And if we compare this bound with what veil gives, which is this one, we see that this one wins when D is at least P to 1 over 4. And of course, it's also better than the trivial bound, which is D times P. Use Woloch's result, we just need to control the absolute irreducibility of this polynomial. And one can do that. One can show that this polynomial is absolutely irreducible if A is non-zero, B is non-zero, and I think A times B is not 1, something like this. And the irreducible case will follow similar discussion. We arrive to the same equation, but now the eigenvalues are in this extension field, and the degree will be P squared minus 1 over tau in this case. So this is the idea of the proof, all right? And now I will start with mentioning a few applications, and the first of them is a bound for exponential sums with matrices. So fix a non-trivial character psi and consider this exponential sum x from 1 to the order of the matrix psi of this multiplication a to the power xb. Now, by work of Korobov, we know that the absolute value of this character sum is at most square root of q to the n, which is non-trivial when the order is at least q to n over 2. But what we want is to obtain a non-trivial bound. So we want to go below the square root threshold. And to state our result, let me introduce this constant kn, which is roughly 1 over 3n squared. And our result is as follows. Let AB be vectors and A be diagonalizable. Assume that these n vectors are linearly independent, and the same these n vectors are linearly independent. Then our character sum can be bounded by the minimum of these two terms. So this one wins in this range, and this one wins in this range. When we are in the irreducible case, we obtain a better bound. And in this case, in fact, the linear independence condition becomes automatically satisfied. So the result reads as follows. Let A, B, and A as before, such that the characteristic polynomial of A is irreducible. Then we have this bound, which I wrote it here in the SLN case, is non-trivial in this range. So q to n over 2 minus n over 2n plus 2. So this is the result that we obtain in this case. Now let me say a few words about the idea of the proof. So some simple manipulation and applying a few times the Hölder inequality, one can show that for integers kl, the 2 times kl power of the absolute value of our sum is at most this quantity, where jk is the number of solutions to this equation, and kl is the number of solutions to this equation. And using the linear independence, here is where we use it, jk, one can show that jk is in fact the number of solutions to this equation, and the same for kl. And now we use what we know. So when k and l are 1, G1 and K1 is trivially tau, and when K and L are 2, we have the additive energy. So we obtain the following inequalities, which relate our character sum to the additive energy. So we obtain that the absolute value of our character sum is at most this quantity when K equal 2 and L equal 1, or when K equal L equal 2, we have this, this bound. And now if we plug in the bound that we have for the additive energy, you obtain the bounds that that I mentioned. But of course, so here, if we can take K and L to be free, then we will win. So we obtain a better bound. And so we can do this for n equal 2. So using the bounds that we obtain for the equation in 6 variable, we obtain the following result. So let A, B, and A as before. We are in the 2 by 2 case. And we have, remember, 2 cases, the split case. So in the split case, and having this linear independence condition as before, the bound reads this way, which is non-trivial when tau is at least p to the 3 over 7. And in the irreducible case, we obtain this, this bound, which is non-trivial when tau is at least p to 5 over 11. So this is what we obtain. Now let me go to the second application, and that is Kloosterman sums over subgroups. So given a multiplicative subgroup of the of this multiplicative group F of the finite field FQ and A, B elements in FQ, we define the Kloosterman sum, the sum over elements in the subgroup. Psi is an additive character, and we have this rational function. Bourgain proved a bound, a general bound for Q equal P for sums of this form, which in particular implies that if the order of the group is at least P to the epsilon, then the Kloosterman sum can be bounded. So here we have the trivial bound, the order of the group, and the saving is P2 minus delta. For some delta bigger than 0, which depends on epsilon, but is not explicit. Since then, the case n equal 1, that is the case of Gauss sums, has received a lot of attention, and there are many results in this direction. But the case of analysis 2 has been in limbo ever since. So let me tell the result that we obtain, which is for free from the previous bound that we had for the exponential sum. So let me take G to be a generator of our group. Let me take A to be this matrix. So we are here in the splitting case. And let me take these vectors A and B this way. Then the previous bound reads as follows, that I mentioned for S2. Let P be a prime and G be a multiplicative subgroup of FP of order tau. Then we have the following bound for the explicit bound for the Kloosterman sum, which is given by the minimum of these terms. Okay, the third application is additive properties of matrix orbits, and I will not enter into details here. Let me just mention that for a given cyclic orbit, which is defined in this way, we give an explicit upper bound for the smallest k such that if we take k copies of this cyclic orbit, we can cover the full vector space fq to the n. And as before, when n equal to n, q equal p, we obtain stronger results because we have the bounds for the equation in 6 variables. And this question is motivated by work of Schoen and Shredov and Bourgain in the scalar case. So they consider the same problem and they give results using additive combinatorics. And the last application, I don't know how many minutes I still have. Okay, I'll be quick because I'm not comfortable talking about it. So this is, I apologize that I'm not an expert in this direction. I feel not quite competent talking about it, but I want to mention what type of result the bounds for the matrix equations gives for this type of problem. So this is the connection that I mentioned that Kurlberg and Rudnick made to studying the equidistribution of eigenfunctions. So let me introduce a notation for n equal 1. We introduce the Hilbert space of functions defined on this ring modulo of residues modulo n with values in the complex numbers and equipped with this scalar product. Define the operators Tn of A, which act on these functions in this way, in this explicit way. Now, given an infinite differentiable function defined on the torus, we consider the Fourier expansion of f, and we define the quantization of this function f to be given by this operator. Right? Now, given a matrix A in SL2 which satisfy other conditions, one can associate with this matrix a unitary operator, which is called the quantized ket map, which satisfy this relation. So this star means the transpose conjugate. And now let me mention what one is interested in. So one wants to study the equidistribution of the eigenfunctions of this operator. And to do so, one defines a discrepancy function. So here we are looking at the average of the function f, which is called observable f in the eigenstate psi, and we compare it. We look how far is from the classical average of f. So one wants to show that when n goes to infinity, this average goes to the classical average. And it is known that this discrepancy function is small if and only if the eigenfunctions are equidistributed. So one is interested to give bounds for this discrepancy function. And let me also note that this difference here is nothing more than the sum over all non-zero vectors, the Fourier coefficients, and this scalar product. And those one reduces giving bounds for this discrepancy function reduces to giving bounds for these scalar products. And taking into account the rapid decay of the Fourier coefficients, it's enough to give a bound for these absolute values of this shape, which will give the results that we need. And now comes the number theory part. So Kurlberg and Rudnick, they connected this problem to bounding the number of solutions to the matrix equations that we have seen at the beginning. And they proved that for almost all n, for all functions f, this discrepancy goes to 0, n goes to infinity. And Bourgain proved a better decay, so proved a power decay of this function for some unspecified delta. And what we do, we give an explicit result of Bourgain. So we make this result explicit. So we prove that for almost all integers n, for all functions f, the discrepancy can be bounded in this way. So how is this connected to matrix equations? It has been clear from the work of Kurlberg and Rudnick and Bourgain that to estimate this discrepancy, one needs a bound for the number of solutions to the matrix equation that I mentioned in the beginning, which is of this type, where here mu is as small as possible and tau is as large as possible, provided that tau is at least square root of p. And this is exactly what we have proved. So let me recall the result that we obtained for f to p. So here mu is 3 we are in the case of 6 variables. And when tau is about square root of p, we obtain these results, which is exactly what we need. And this will lead to the bound that I mentioned for the explicit bound that I mentioned for the discrepancy function. So I think I'll stop here. Happy birthday, Andrew, and all the very best.
Comments and/or questions for Alina?
I don't think that the method gives an explicit bound. You mean the power delta? Yeah, I don't think that the method gives an explicit bound.
And can you compare the bound, your bound with Bourgain's one for Kloosterman sums over small subgroups? Can you compare the bounds between Bourgain and yours?
So, well, Bourgain's bound is not explicit, first of all.
Yeah.
While ours it's explicit, so we give an explicit bound. Kloosterman sums. So again, for Kloosterman sum, this delta is not explicit in his work, and I don't know how to make this explicit. Not that I know. So maybe.
What kind of other exponential sums over small subgroups can you expect to bound?
Sorry, once again.
What kind of other exponential sums over small subgroups can you expect?
You can,
to bound?
for example, you can play the same game with Gauss sums, and you can obtain results in this direction as well. And in fact, we do. And so maybe you can do more types of exponential sums, but I have not looked into this. So for sure, it gives results for Gauss sums and for Kloosterman sums.
Any further questions for Alina? If not, let's thank Alina again.